I would like to use some interesting cases where quality was somehow neglected, and it led to quite big consequences. And show you on these examples why the quality is important, as always. So, can you imagine the worst that could happen? For example, a scenario where a single sensor failure can lead to catastrophic consequences. When you have a state-of-the-art technology that is designed to make the system safer, but instead it contributes to the loss of 346 lives and costs the company over $20 billion. Yeah, this really happened in our recent past, and today, among others, I will show you this one, and I will show you how quality assurance and thorough testing could have prevented these tragedies. As you already probably know, the quality is kind of important. If I go into more details, I would say that quality and QA processes are critical in disaster prevention. When set up correctly, they help with early issue identification, ensuring systems quality and integrity. They also can promote safety culture, and they should also encourage continuous improvement. And when quality fails, my goal is to show you that even seemingly small error can lead to huge disaster. In some industries, even a tragedy. I have 3 examples prepared for you to demonstrate impact of quality issues. One is Ariane 5 rocket. Second is Mars Climate Orbiter, and the third is Boeing 737 MAX catastrophe. So what happened with Ariane 5? On June 4th, 1996, ESA launched the Ariane 5 rocket for its maiden flight. This was meant to be a milestone in European space exploration because Europe needed independent access to space and its own ability to launch satellites, and not to rely on space agencies of other nations. So if you go back into history, the initial preparatory work started in 1984. Then 87 program was officially approved. 88 full-scale development commenced, and 8 years later, the first launch attempt occurred on June 4th. But as you already probably know, it ended with a big failure. And what happened? The rocket, after just 37 seconds after start, it veered off the flight path, and it disintegrated under aerodynamic forces, and it had to launch its self-destruct system, which was a safety measure to prevent the rocket from potentially causing damage on the ground. So what were the causes? So why this catastrophe happened? Well, the root cause, or the main cause, was that the navigation software was reused from older Ariane 4 rocket, but it wasn't adequately adapted for the new model, for the Ariane 5. The alignment function of inertial reference system was still active after takeoff, and this served no purpose for Ariane 5, which was a big design oversight. And also another important thing is that Ariane 5 had vastly different flight profile than Ariane 4. The increase in horizontal velocity was approximately 5 times greater during the first 40 seconds of flight. And what happened with the alignment function was that the critical error occurred when converting horizontal bias that was calculated from the horizontal velocity, which was much higher than for Ariane 4. And when 64-bit floating point number was converted to 16-bit signed integer, it resulted into overflow. And the trouble is that this overflow error caused a hardware exception, which halted the inertial reference system, which navigates the rocket. But it also halted its backup system that was intended for redundancy. So the rocket had no way how to navigate itself. And when the analysis was performed, also another thing that was a big big problem, that there were 7 critical variables in the navigation, but only 4 of them were protected from overflow, against overflow, and the others was just assumed that they would stay within a reasonable range, which was valid for Ariane 4, but not for Ariane 5 because of different trajectory. It wasn't possible to protect all the critical variables because it wouldn't meet the performance target for the computer. It would result into heavy load on the navigation computer. And what was the loss? The loss was in total $370 million, and it also cost a 2-year delay. Just 2 years later, it took 2 years for another launch that was finally successful. So this catastrophe is a bit known, and it serves with interesting lessons. So the first lesson is that if you reuse any component, hardware, software, you definitely should do a thorough review if everything is as it should be. In this case, the software wasn't properly adapted for new flight characteristic, and so what should have been done is the software should be taken and thoroughly reviewed and tested for the new conditions, for the new trajectory, and so on. Also, another thing that should have been done and wasn't was comprehensive system simulation, because what was done was only simulated output was used, not actual system or detailed simulation, and that's the reason why the flaw wasn't detected earlier. So it's really important in critical cases to test end to end, and in cases like rockets and so on, also with real or closely simulated hardware. And the third one is they should have tested with specific data that was specific for Ariane 5 rocket, because these tests didn't use Ariane 5 specific trajectory data. And so the software wasn't actually checked under actual flight conditions of this rocket. So don't forget to test with the data that reflect the real world usage. Actually, after the incident, when the analysis was done, simulations using actual Ariane 5 flight data actually showed the failure, accurately showed the failure, and this shows that if they would use a realistic testing scenario, they might have uncovered this problem that cost too much. That was the first example. The second example is Mars Climate Orbiter. This was part of Mars survey program. Its purpose was to study Martian climate and atmosphere, and it was collaboration between NASA and Lockheed Martin. It was launched on 11th December of 1998, and after 9-month trip to Mars on September 23rd, 1999, spacecraft approached Mars to enter orbit. but the trajectory was, of course, and the spacecraft entered Mars atmosphere, the Mars atmosphere, and the mission was completely lost. So what were the root causes in this case? First, it was quite big miscommunication between NASA and Lockheed Martin. And it turned out that they didn't have clear standards and the same standards for units of measurements. And also didn't cross-check the calculations with these units. Because these two companies used different measurement systems. Lockheed Martin used English units, pounds for thrust calculations, and NASA used metric units, newtons, for trajectory calculations. And actually, there was no system in place to catch this discrepancy, which is crazy. And also, the testing and verification process was inadequate. And the integration testing did not catch the unit mismatch and simulation. And also, it wasn't caught the problem because the simulations didn't use actual hardware or sufficiently detailed models. And the impact was not just financial loss, which was 125 million, which is like cost of the spacecraft, years of research and development, launch costs and operational costs. But it was also a significant setback in the overall budget and planning for Mars exploration initiatives. It had impact on future missions because NASA had to reevaluate its procedures and protocols in the program. It delayed the timeline for further missions and so on. And also, well, it resulted in the loss of scientific data because the Mars Climate Orbiter was designed to study Martian weather, climate, and atmospheric conditions, including monitoring dust storms and temperature. And its destruction resulted in the loss of valuable data that could have advanced our understanding of Mars climate and potential for habitability. What were the lessons learned in this case? So again, integration testing, thorough testing of the entire software system as a whole, including all components from different teams and partners. Again, usage of actual flight trajectory data and simulation to accurately represent real mission conditions. And integration tests also should cover all critical calculations. The problem was apparently in standardizing measurement units because the single standard system of measurement units wasn't established across all teams and contractors involved in the project. And also, this should be all clearly documented and communicated from design to execution. Also, the cross-team communication wasn't as good as it should be, and regular cross-team reviews of critical systems and calculations in the development process could help uncover this error. That was the second example, and the third example, which is more recent, or most recent from these three. You might remember it. It's concerning Boeing 737 MAX airplanes and what happened there. So there were two fatal crashes of this plane, where the 346 people were killed in both incidents. And in both cases, these planes crashed into the ground shortly after takeoff. And after that, due to safety concerns, all 387 Boeing 737 MAX planes were grounded for 20 months, which affected 8,060 weekly flights by 59 airlines. I would like to go through the timeline. It was on the October of 29th when occurred the first crash. It was the first major incident involving the 737 MAX plane. The investigation lasted from November to February, the initial investigations, and preliminary reports suggested issues with the maneuvering characteristic augmentation system, MCAS, but Boeing and FAA, the federal agency, maintained the aircraft. They said that essentially it is safe to fly. But it didn't take long, and in March the 10th, 2019, there was another crash with 157 fatalities, second major incidents within 5 months, and the global response was pretty quick. Several countries and airlines began grounding this type of aircraft. From the beginning, initially FAA resisted the calls for grounding, but it took just 2 days for the emergency order, and all these all these aircraft of this type were grounded worldwide. So on March 18th, there was complete grounding of all these airplanes, and as I said, it took 20 months until they were permitted to fly again. So what were the root causes in this case? In this case, it was even poor design or poor decision making during the design, because this airplane had larger engines than Boeing 737, and they were mounted forward on wings, and this altered plane's handling characteristics. And the Boeing didn't want they just wanted to cut like go through a shortcut, not to design absolutely new plane, and with all these regulations and improvements and so on. They just wanted to improve the plane they had and go sell it. So they chose this way, and so the engine placement was a big issue for the handling characteristic, and that was why the MCAS system was designed, which should prevent stalls of the aircraft, because the changed aerodynamic resulted into higher danger aircraft stalling. The problem is that MCAS relied on the data of single sensor. There was no redundancy there. Planes took off. Something happened there. The one sensor that was sending angle of attack data to the system, to the MCAS, started to send some garbage data, and the MCAS system interpreted it that it should push the nose down. So the system started to push the nose of the plane down. Pilots were like unable to control the aircraft. They were following emergency procedures. They power to the stabilizer trim motors, but they were unable to maintain the plane's altitude, and the planes ultimately crashed to the ground. The estimated loss is really huge. It's around $20 billion, which means like direct and indirect costs. The direct costs from grounding, also lost orders and revenue. A lot of orders were just cancelled. And also it was a big reputational damage for the company. So what are the lessons learned in this case? You should always make sure that you prioritize safety over cost cutting. The decision to modify existing design rather than create a new aircraft was just driven by market pressures and cost considerations. And apparently it wasn't a good decision. Also, the risk assessment redundancy wasn't as it should be, as the MCAS system relied just on a single sensor, which created a single point of failure. And also, thorough testing and training wasn't in place. Again, comprehensive testing, including edge cases and failure scenarios, could have uncovered this problem. And pilots were initially not even informed about the system MCAS and trained how to handle its malfunctions. Also, transparent communication would help, because Boeing's initial reluctance to ground the aircraft and fully disclose the extent of the problem probably caused the second aircraft disaster. And also, in this case, it's like regulatory compliance and ethical responsibility of the company and the agency, FAA, because FAAs relied on Boeing for safety assessments due to lack of resources, which is kind of crazy. And yeah, we always should remember that there is like a responsibility in some industries to prioritize user safety. Also, for this eventually led to improvements and learning. So these disasters led to complete overhaul of Boeing's safety culture and processes. So hopefully such big disaster won't happen again. And this disaster serves as a reminder that even industry leaders can face catastrophic failures when quality and safety are compromised. So what are the key takeaways across the incidents? Design without shortcuts. Prioritize long-term quality over short-term gain, like in the case of Boeing. When you if you look at it from our software perspective, if we are rushing features and cutting corners in development to meet deadlines, this can lead to critical oversights. Another thing is redundancy and risk assessment as the multiple layers of protection. When the system is critical, redundancy should be always considered, like in the case of Boeing, the single sensor. Also, the risk assessment, the identification of single points of failure should be also a concern. And if we take it to a software world, it's like a dependence on single data source or service without any fallbacks or high availability. So we always need to focus to remember to think about fault tolerance, redundancy, graceful degradation in critical systems, and so on. For example, circuit breakers, retry mechanisms, fallback strategies, especially in distributed systems. Another thing is clear communication. All teams should align all specifications and changes. The communication is important, as in the Mars Climate Orbiter example. So, for example, in software world, it's important to transparently communicate about known issues, limitations, and potential risks in software products. And also, if we want to build trust with users, we should communicate honestly and timely about problems and their resolutions. Another thing is data validation. Critical systems have to be robust and have to have robust handling across systems. So validation of the data, like input validation, error handling, consistent data formats, and so on, like for example in Ariane 5 system. Again, comprehensive testing, don't forget to simulate real-world conditions. For example, Ariane 5, Boeing, all three examples show this problem. So you should focus where it's important to use integration testing, system level testing, end-to-end testing, and so on. And the final takeaway, also, you should foster a culture of safety and improvement to ensure continuous learning. So like in the case of Mars Climate Orbiter in NASA or in Boeing, we should encourage blame-free culture for reporting issues. We should learn from our failures, continuously improve our development and testing process. And what we could do in our software world, we should do regular code reviews, postmortems. We should analyze them. We should share lessons learned across the organization. Because culture of continuous learning leads to long-term quality improvements. So conclusion, quality should be a mindset. It's not just a phase. It's not just ticking some boxes. It's a continuous process which should be ingrained in every aspect of the software development, from the design to maintenance and updates. And companies need to shift from how quickly can we ship this to how can we ship this safely and effectively. Because consequences of overlooking quality can be really grave. Ariane 5, 370 million, Mars Climate Orbiter, 125 million, Boeing, 346 life lost, and 20 billion in losses. And these weren't just bugs, but systemic failures in quality process. And you can see that even small oversights can cascade into significant consequences, both financial and human in some industries. If you look into quality as investment, you should look at it as an investment and not as a cost, because time spent on quality upfront saves time, money, and potentially lives in the long run. You should know 100 rule of quality management. When it costs $1 to prevent a defect, for example, during the design phase, it costs $10 to correct the defect, for example, during the development testing phase, and it costs $100 when failure occurs, for example, fixing a defect after release. And I like to quote Benjamin Franklin, a very nice quote: "The bitterness of poor quality remains long after the sweetness of low price is forgotten." Because if we are pushed in the crazy deadlines, this often leads to technical debt, which compounds over time, and this simply has consequences. So originally this was just first half of the presentation, but I saw that it's already quite long. So I will continue with the second presentation where I will show the real world case study from Heureka that cost us 5,000 euros. And I also show you some practical strategies how you can embed quality in your workflow. So remember joining us next time and help us prevent disasters even before they happen. Thank you. Thank you for your attention. And also I have to thank Eva Podbrska from Comax for inspiration, because some time ago it was her who had a presentation about Ariane 5 rocket. So I took that example and found two more to present these catastrophes. Thank you.